Okay, so finally the topic of basis of vector space. Bases is the plural, and we want to start right off with a definition. So a set of vectors, a set of linearly independent vectors that spans all of the space, the entire space, that spans all of V. V is the big vector space we live in, is called a basis for V. Okay? So a basis is a set of vectors that has two properties. One property, they're linearly independent. Another property, they span the entire space, not just a subspace. Okay? Let's do some examples. So here are some examples. Let's look, so example 1, let's take V to be R3. Vectors with 3 entries, let's think of them as column vectors with 3 entries of real numbers. Okay? So let's look at the set where U1 is going to be 1, 0, 0. U2 is going to be 0, 1, 0. And U3 is going to be 0, 0, 1. Let's look at the set U1, U2, U3. So first of all, in order to say that these together form a basis for R3, we need to show two things. We need to show that they're linearly independent. Are they linearly independent? So let's run the arguments without writing everything down. What does it mean for them to be linearly independent? Well, there are two ways to check that we discussed. One, you can straighten them out as rows of a bigger matrix, a 3 by 3 matrix, right? And check if after you do row operations and reach the echelon form, if there's a row of zeros, right? But this is already, if we straighten them out, we get the identity 3 by 3 matrix, which is already in reduced echelon form and has no 0 rows, so they're linearly independent. Another way of determining that they're linearly independent is taking a linear combination, assuming that it equals to 0, and checking if the system that shows up has a solution. Okay, it's going to be a homogeneous system. Does it have a solution? Remember, those were the two ways, but either way you can easily verify, we even said all the details, that this is a set of linearly independent vectors, right? So U1, U2, U3 as a set is linearly independent. Good? So that's this property. Now we have to check, does it span all of R3? Is the span, can any vector in R3 be written as a linear combination of these three guys? And this is easy. So is linearly independent and spans R3. Why does it span R3? Let's take any vector in R3. It's going to be of the form some A, some B, and some C. This is a general vector in R3. And I can easily write it as a linear combination of these three guys, right? I'm going to write it as A times 1, 0, 0, plus B times 0, 1, 0, plus C times 0, 0, 1. There you have ABC as a linear combination of U1, U2, and U3. So do you agree that this set is a basis for R3? Good? Okay. So we're listing some examples. The next example is going to be just generalizing this idea to something more general. So in general, the set, which includes 1, 0, 0, and then 0, 1, 0, dot, 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 0. And then 0, 0, 1, 0, dot, 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 0. And so forth, all the way up to 0 and 1 in the last coordinate. This set is a basis for not even Rn, take any field and take n tuples over that field. Okay? Why? Well, they're linearly independent. Just straighten them out as row of a big n by n matrix, and you're going to get the identity matrix, echelon form and no zero rows. Okay, so they're linearly independent, just like in the toy example in R3. And they span everything, because you can write any general vector in Fn, a, b, c, d, e, f, g, all the way to whatever n is, hopefully less than z, right? But then you would write a1, a2, a3, and so forth. You would write it as a1 times this, plus a2 times this, plus a3 times this, all the way up to an times that. Do you agree? And this basis also has a name, so it's a basis for Fn called the standard basis. Okay? It's standard. Okay. Here's another example. Let's look back at a good old R3, and let's look at a different collection of vectors. So those were called U's, so let's call it V. V1 is going to be the vector 1, 1, 0. V2 is going to be the vector 1, 0, 1. And V3 is going to be the vector 0, 1, 1. So these are three vectors in R3. Question: do they form a basis? Okay. Well, we need to check. We need to check if they're linearly independent, and we need to check if they span all of R3. Now, to check if they're linearly independent, we could easily do it, but we did it. It was a previous example. Okay? So we verified previously, 1 or 2 lessons ago, that V1, V2, V3, this set with these exact vectors is linearly independent. Okay, I don't know if you recall this precise example, but you can look it up. Okay, we did it. Okay, what we didn't do is show that it generates all of our 3. Okay, so we need to check to take a general vector, a, b, c, and show that we can write it as something times this, plus something times this, plus something times this. Okay, in general. And let's do it. Let's show that they span R3. So we will need a bit more space. So what does it mean that they span R3? I need to take a general vector a, b, c and show that I can write it as a linear combination of v1, v2, and v3. Now, I don't know what that linear combination is going to be a priori. In the first example, it was obvious. It was a times the first one. It was very easy. But now it's not. Now we need to actually do some calculation. So are there x, y, and z such that ABC equals x times v1 plus y times v2 plus z times v3? Is there a solution to this system of equations? If there is a solution, then the answer is yes. We can write every ABC as a linear combination of the 3. Do you agree that this is the question that we're asking? Okay, so how do we check if there's a solution? So let's write it. We need to check if this system has a solution. Do you agree? And we know how to do that, right? So let's write it in the augmented matrix form. So we're going to have what? 1, 1, 0, A. Okay, does everybody understand what I'm doing now? What's going on? Everybody? Good? Okay. 1, 1, 0, A, 1, 0, 1, B, and 0, 1, 1, C. And we need to start doing row operations. Okay, so let's do it. Do I want to do all the details? Sometimes it's fun. It's okay, you're saying, right? You can do it on your own. Okay, let's not do all the details. But, so we have a way of not doing all the details, right? Skipping all the steps. So you can do it, but do it all the way to the canonical form, to the reduced echelon form, okay? And we know by a previous theorem that we quoted that doesn't matter which steps you take, the reduced form is unique, okay? So if I did it differently in my notes and you do it differently, if you go all the way to the reduced form, there's only one, okay? So you're going to get in the reduced form the following: 1, 0, 0, and here you're going to get A minus C plus B divided by 2. And then 0, 1, 0. And you're going to get here C minus B plus A divided by 2. And then 0, 0, 1. B minus A plus C divided by 2. That's the reduced form, the canonical form. Okay? So what this means is that, well, the rank of A is the same as the rank of A star, right? And it equals n, which was 3 here, right? Therefore, there is a unique solution, and it's right there staring at us, right? X has to be this, Y has to be this, and Z has to be this. Do you agree? Okay? So, conclusion: A, B, C, any general vector in R3 can be written as A minus C plus B divided by 2 times 1, 1, 0 plus C minus B plus A divided by 2 times 1, 0, 1 plus B minus A plus C divided by 2 times 0, 1, 1. And you can easily verify this. Okay? Check the calculation. That's easy to do. Okay, so is A equal to what we get in the first coordinate? So we have A minus C plus B divided by 2. So there's a minus C divided by 2 plus C divided by 2. Cancel. Plus B divided by 2 minus B divided by 2. Cancel. And A divided by 2 plus A divided by 2. So it's A, and this one contributes nothing in the first coordinate. So do you see that the first entry is indeed A in both sides? And likewise, you can check for the other entries. Good? So, let's go back to the previous board. We verified previously that this is a linearly independent set. We just showed that they span everything. So this set of 3 vectors, v1, v2, and v3, is a basis. And now you can see that the word a basis is indeed the right word to use. It's not the basis, because we just found 2 of them, right? In the first example, we had those u1, u2, and u3, which were totally different bases for R3. So bases are not unique, okay? You can have 2 sets that both are linearly independent and span the entire space, even though they share no 2 elements. Okay, there's no element that's the same in both. Okay, so a basis is not something unique. Okay, here's one more example. So this would be example 4. Take, for example, V to be polynomials of degree less than or equal to n over R. Remember this notation? Polynomials of degree less than or equal to n over R. Okay? So, and let's take the following set. I'm going to take 1, this is a polynomial, right? X squared, all the way up to x to the n. So this is a set of n plus 1 polynomials, right? And I claim that this is a basis for Rnx. How do you show that it's a basis? Well, you need to show two things. You need to show that this set spans everything. That's completely straightforward, right? If you want the polynomial a n x to the n plus a n minus 1 x to the n minus 1 and so on, well, just take it. It's a linear combination of these guys. Do you agree? Okay, so obviously these polynomials span any polynomial. Any polynomial in this space is a linear combination of these, right? And are they linearly independent? Okay, intuitively, can any one of them be written as a linear combination of the others? Answer is no. Formally, how do you check that? Well, we know various ways to check it. Two ways. One, you can set it up as a system of equations, ask the correct question, it's going to be a homogeneous system, and see if it has a solution. Two, think of the coefficients, okay, and straighten them out as rows in a big matrix. Okay, so what are the coefficients here? Here the coefficients are 1, 0, 0, 0, 0, 0, 0, 0 for all the other powers of x. Here, for x to the n minus 1, it's going to be 0, 1, 0, 0, 0, 0, 0, and so on. Those are the coefficient vectors for these polynomials. Straighten them out in a matrix. They're already the n minus 1 by n minus 1 identity matrix. No zero rows, already in reduced form, so they're linearly independent. Okay? And this is hiding a more, we already mentioned that there's something hidden here, the fact that we translate these into rows, into row vectors, and that we're almost there. We're almost able to say that fact in a precise way. Okay? So do you agree that this is a basis for the polynomials of degree less than or equal to n? Okay. And in fact, this is the standard basis. It's just the standard basis that we had in example 2, disguised for polynomials of degree less than or equal to n. Okay? Okay, so a quick summary of the examples that we had. 1, checking that something is a basis amounts to nothing more than checking if it satisfies the two properties in the definition. Is it a linearly independent set? And does it span everything? We know how to do both of these. Okay? Both normally translate to solving some relevant system of equations. Not the same system. You have to understand what you're doing. Okay? 2, bases are not unique. A space can have many different bases. Okay? Okay, so coming up next, dimensions of a vector space. So here, for example, you would want to say that this space has dimension what? N plus 1. Because we need n plus 1 guys to span it. Okay? That's the idea. How many guys do we need to span it? Okay? How many guys do you need to span it optimally? You can always take 15 more polynomials and not make the span any bigger. Okay? So what's kind of an optimal spanning set, a basis? How many elements does it have? And the first statement that we're going to make is there could be many bases for the same vector space, but they're always going to have the same number of elements. You can't find one basis with 3 elements and one basis with 4 elements. It's an invariant. Okay? You can have many bases, they always have the same number of elements, and that's going to be the dimension. Okay? Coming up next.